So let's move ahead with the last part of this discussion. Tangents. Not getting into too much definition of integrals. Already know what integral means, especially definite integral. Imagine if I have a integral a to b, I have continuous function defined on it. Okay. Then for a definite integral will be area, including area under curve. The question is that how do we compute it? Okay. We know that before what we do that we partition is b into basically some number of subintervals. And then we say that okay, subintervals try to draw the rectangles which approximate the area. How can I draw rectangles basically? What's the recipe behind drawing rectangles? What kind of rectangle I should draw, for example, in the first unit?
Height. If of A is the height of the rectangle,
Where is the height of?
and A plus
How we draw the rectangle? What should be the height?
F of A.
How should we decide?
3%.
Take a point in the
Which point?
Which
one? F of A. Take this point on the curve and then
8 points.
draw a rectangle.
Yes.
Okay. What next?
F of A plus H. The second.
Then take the next point. And then
F of A plus H height.
take this point
Yes.
and draw a rectangle. Okay. And then
F of A plus
the
2H.
point is drawing the rectangle. And then just keep on doing the path. Take this kind of point, draw a rectangle. This kind of point. This kind of point. Draw a rectangle. This key point, and so on and so on. That's what we do. Now, one of the obvious trouble with this figure is that it's not a good approximation. This is lots of area. This chunk is missing. This chunk is missing. That's over actually.
It's
This part is missing. It's not a good approximation. So, what was our logic? The logic was that we have this curve which is defined over the interval A to B, and we took the and we partitioned
Very small and check.
and then took what? Took the left hand point. So always left hand. So draw a rectangle based on left hand. Now, the other has suggested that other recipe could be that okay, make this partition more bigger. And then do what? So we do the same, take the left hand point draw rectangle, left endpoint, draw rectangle. Okay, it's better than previous, but still you have error. Keep on doing it by that way. I can approximate for the area by these rectangles. There is going to be. I'm interested in basically those recipes for which
Continue.
error is
Zero.
Minimum.
0 or minimum. 10 to 0. So this was recipe. I will take kind of left hand. If I take the right hand point of the same both sides, the same curve, we're going to have what? So it's like, okay, take this height and go out. And then bring this one and
First.
go out. And so on and so forth. What would be trouble in this case then? It's like
Then you can do what you
where
can
there's
do.
overestimating in some part. So it's like here it was underestimated, but here it's overestimated. You have troubles basically in both cases. So what would you like to do? So basically think of creating such a machinery which can kind of help us to approximate the area much better. So we want to make this theoretically precise. We just don't want to draw pictures, but we want to do mathematics. Let's begin with the mathematics which can kind of help us. It's just like from these two pictures, so it's undecided that what should I do? It's like this is underestimating, this is overestimating. Something crazy going on. So what should be the consistent way to approximate the areas?
Take each approach to 0, sir. Small.
Change.
Change.
Okay. Which actually means that you increase the number of intervals.
Yes, sir. Infinite number.
That's a recipe, but give you more precise version of things. So imagine I have a function, maybe I closed interval A to B, a subset of R, and I have P, the set actually comprises of, I'm going to call a partition of the interval. P is what? It's a partition of interval A to B. And what does this contains? This set contains the points actually, in which, so it's like a finite set, which things have the interval have the partition at these endpoints where what are these x naughts, where this x naught is A, which is one point, and all these points are strictly less than each other. In other words, all these points, in the interval, lie on, so it's like one point is at
Left.
like x1 is at the right of basically
Yes, sir.
x1, and x2 is on the right of x1, and so on and so forth, and xn is what we call b. Okay. Imagine I have a function f. So the function defined on this interval, and this function is a bounded function. Okay. Remain continuity, just assuming boundedness. These functions are bounded. So continuous functions are included. This can be a continuous function. Then I'm defining one of basic things. So on each subinterval, in other words, I have this closed interval A to B, and X naught is A, and X1 is B, and these are the points basically. These are the points basically sitting between A and B. Okay. And on each such interval, I'm defining some notion. So in other words, if I take an arbitrary interval, xi minus 1 and xi, okay, then I'm defining some notions. By small mi, okay, I mean infimum, okay, of infimum of the
Exercise.
what? Of f of x. It's like infimum that function takes between interval xi minus 1 and x. X plus that x is xi minus 1 and x. So by mi I mean what? Infimum. So it's like what is the smallest value that f can achieve in this whole interval? And by capital Mi, I mean supremum of f of x such that x is in this interval xi minus 1 and xi. We have more notations that I'd like to define. Now, where are actually we heading? So, redraw something. So our approach is going to be this. We can approach this problem in two ways. Imagine I have a B, and I have partitioned it endpoints. This is x naught, this is xn, okay, it's x1, x2, and this is an abstract interval, you say x2, that's an abstract interval xi minus 1 and so one approach is this, rather than taking left hand point and right hand point, take an interval and see where is the minimum, what is the smallest value within this interval that function takes. So what is the smallest value that function takes here for example? So it's at the left hand.
If of
Okay. Now draw box of this minimum height within this. Okay. And how about this one? Here,
if of x.
the width is going to be same as
Yes, sir.
the length of the interval. Width is going to be same as length. And similarly here,
If of x ends.
so take the smallest value. Which is the smallest value here?
If of x.
About that. This is the smallest value. Take this height and how about in this interval? The smallest value is here for instance. Okay. And in this interval, the smallest value is. And similarly, in this interval, smaller value is on this side, and then maybe the smallest value on this side. this one goes here, this interval, the smallest values here, and so on and so forth. So we can you see that what's going on now? What is the difference between something that we did previously and now? So there we just took left and right hand endpoint, left hand points and right hand points of in a subinterval just blindly. Okay. So what is the difference between this approach and this approach? Can you know which is more consistent actually? Just think about it. The lower one is more consistent. Why it is consistent? Now here you don't know that. I mean, sometimes you are underestimating. In some part you are underestimating area. In some part you are overestimating it. But if you always take, for example, minimum, okay, then you will always be below basically your area, approximated area is going to be below the original area. Because that's one of the good things that we have. But the second thing is, how can I improve my area now? How can I improve my area? In such a way that this basically die, okay, gets closer to the original area. So what should be done? By increasing the number of rectangles. In other words, adding new points basically. For example, if I say that which are basically the intervals, where should I add basically some new points? All basically. There is trouble in almost all of them. So add new points. So imagine I'm adding some new point, not necessarily in middle. Okay. I'm adding new point. So when I'm adding new point, I got a new partition actually. So this partition P, which is this basically, has been now improved that. This becomes a subset of a new partition. Obviously, you need to give new names. Y0, Y1, Y2, Y3, and so on and so forth. Okay. And see that whether this helps or not. And we're going to do the same. Okay. We're going to do the same act. First, let me define something, which is, for example, I'm defining. File here. Get rid of the top. So for a given partition, imagine I haven't drawn the original points. I haven't drawn these new points, and I have the previous partition, like this partition actually. So I would like to define this notion, which we call lower Riemann sum. And I denote it by LF, so it's like a lower Riemann sum of F according to the partition P. So this LFP represents basically area covered by all these rectangles. Now how you can compute the area covered by all these rectangles? What you need to do? You have to multiply the heights which are infimums.
Yes.
With what?
With
Each of the width activities. So in other words, for the partition B that you have, you're going to have what? Sum from, for example, I equal to 0 to n or n minus 1. What is that? N,
yes, sir.
it should be n. 1 to n. And mi is what? In the interval. So for example, ith interval, mi is the infimum.
Yes.
It's the smallest value that f takes actually. And multiply it with
F of
xi
xi.
Yes.
Or you can do, so for example, xi minus 1. But if
It's not a start.
what?
It's not a start.
Yeah. So should be xi plus 1?
No start.
No, ठीक है.
So it's positive.
ठीक है, is it making sense?
Yes, sir.
So this is representing basically what? Sorry. Okay. But we know that this is not a good approximation of this nonlinear area. So what we need to do, we need to improve the partition. And we had previously this partition, and now I'm saying that, okay, imagine I'm now having a new partition, P1, P bar, whatever you call it, and it comprises of new points actually. And call these points as y0, y1, y2, example. Y0, y1, and up to. How many are going to be these points actually? Okay, whatever. Some m actually. M is bigger than. I don't know. Okay. But this new partition comprises all of these points as well. Just like x0 is y0. Okay. x1, y1 is a new addition, while y2 is x1 and so on and so forth. And we did what now? We're doing the same. So I want to compute with this new partition, I want to compute what the lower Riemann sum, and I want to see that with this new partition whether my area is going to improve or not. Okay. So take the same endpoint and this and take the this endpoint and you've got this endpoint. See that already this part has been saved now. It's added to my
Yeah.
the Riemann sum. It's going to be added to the Riemann sum. And similarly, this one, I don't have colored charts, otherwise you have seen explicitly, but you can already see that, the area is going to improve. So because this LF, P star, or maybe P bar, okay, is basically what? MI, for example, or the MI bar, because these MIs are basically what the infimums over with respect to this partition, so you need obviously represent them with some new notation and multiply them with yi minus 1, where I is from 1 to m. Agree? So what we can do? So we can say, okay, what is the relationship between this P bar and previous P? So we know that P is contained in.
Yes, sir.
P bar. So what we're gonna say? We're gonna say that P bar is a refinement for Pn. That's it. Is what? Refinement for P. And we refined the partition, made it more better. Like fine. There can be lots of such partitions. There can be lots of such partitions. I don't know how many different partitions. It's not necessary that we keep on we just take one partition and keep on slicing it. I can have a completely new partition as well at different points, which is more better than previous ones. So, you're gonna see that I can always find one partition. Okay. I can always find one partition in such a way that if I take the lower Riemann sum, okay, of that partition is going to be really equal to what? Area under the curve that you want. Okay. But how can I have that partition? So the matter is basically to take the supremum of these LFPs. Just think whether this LFP is going to be a big number or this LFP is going to be a big number. The low one is going to be a big number. Because it includes this part and many other parts. Okay. So what we can do, we can say that okay, you can have lots of partitions of the interval A to B, but take the supremum of all of these LFPs, and that supremum is going to give you the expression. How about thinking other way around? Just think about it first. First, if this description is making sense to you, then the theory is going to make sense. Imagine instead of taking supremums, now I'm taking infimums. Now I'm taking supremums. Within interval, supremum. So if I take supremum, what is going to happen on each of them?
The area is poor.
So it's going to kind of give you overestimate actually. It's going to give you what? Overestimation of the area. And you make your partition refined by the same logic. You will see that this error that basically this upper Riemann sum that we are going to define contents is going to reduce and reduce. Going to reduce. So if you take, for example, big chunks, like if I take, I can make it better to make it. Imagine I have B, and then I have a similar kind of a function, okay, and I have big partition. Then a few points, okay, and then each of subinterval I take supremum. So it's like what is the biggest value of f in this interval? So it is this one.
Yes, sir.
And draw a rectangle of this one. Okay. How about here? Have something similar. Here. How about here? Now this sum, okay, which you take through supremums in each subinterval, it overestimates basically, or over approximates actually the original area. And now just think about it, if I refine the partition, what's going to happen? So in this interval, so you have this as the supremum, okay, and hence you're going to have this rectangle. Okay. And how about this interval? So this is going to be the rectangle. So what happened now? Now this part is removed.
First instant we are choosing the supremum, then we are taking sums. Okay, first instant we are taking the supremum, and now we are taking partition interval between there.
No. The point is this. What we did previously, we said, okay, on each subinterval you have a choice. I can choose infimums and supremums. So if I take infimums on each subinterval and draw the rectangles according to them, then my area that is going to come through those rectangles is always going to be the below original area. Okay. And we saw, at least we intuitively saw, that if you take the supremum of the lower Riemann sums is going to give you a better approximation of this area. And now I'm saying that, okay, I can do the precisely same objective, but in another way. And the other way is that take the supremum over each subinterval, okay, and draw a rectangle. And we saw that by that